we were discussing regulator, voltage regulator, and we had seen how a reference, Zener reference could be obtained, and that could be fed as one input and output voltage as another input to the base emitter junction. So, that this current, the error current is going to adjust the drop across the transistors, so as to keep output constant at a value of V z minus V gamma. That simple regulator we had discussed in detail. Now, obviously, one limitation of that circuit is that V naught was not adjustable once V z is fixed, and also V naught was not exactly V z, it was V z minus V gamma, and it was dependent upon the base to emitter junction potential difference. So, we would like to get rid of all these things and use an error amplifier, and the error amplifier we said could be an op amp comparator or simple differential amplifier. So, now we will use a simple differential amplifier, which is a crude version of the op amp itself. So, this is the difference amplifier here, and the voltage that is developed across the load of the differential amplifier, that we will see, is going to be taken to control the base, that is collector emitter voltage drop of the transistor. So, earlier this was compared with this, and that became the input. Now, this and portion of this that is, this is being compared with, let us say, R 1 by R 1 plus R 2 times V naught, portion of the V naught output voltage. This is a comparator which is nothing but a differential amplifier here, and let us say we are putting this as I naught. This I naught could be a current source which we can derive, we know how. So, this could be directly connected here. So, essentially we see here either an op amp or a differential amplifier could be used. From here to here there is no phase shift, from here to here there is a phase shift of 180 degrees. So, this is minus terminal of the op amp, this is plus terminal of the op amp, this is the output of the op amp. So, the output of the op amp directly goes to the base, right. This structure we had earlier indicated as the basic structure, which will involve a voltage reference, a series pass transistor, and a comparator, okay, and the load. So, actually the comparator is comparing the voltage reference with portion of the output voltage. If therefore, this is a negative feedback structure, then if this is V z, V z should be very nearly equal to V naught into R 1 by R 1 plus R 2. If the gain of the open loop gain of the amplifier is very high, then this voltage should be same as this voltage. So, essentially you can see that this particular structure is a very crude operational amplifier using a single supply. The input voltage itself is biasing this operational amplifier. So, one end of the op amp is connected to this end supply, and the other one is connected to ground. Okay. Output goes to the base of the transistor. So, you will see that this configuration is normally available as a voltage regulator IC. In the IC manufacturers have a differential amplifier and a series pass transistor and a voltage reference as part of the IC. So, this is a crude picture of a voltage regulator integrated circuit. So, now let us see what exactly happens. V z is equal to V naught into R 1 by R 1 plus R 2. So, V naught therefore, essentially is equal to 1 plus R 2 by R 1 times V z. So, depending upon V z, once V z is fixed, we can always find out what the R 2 by R 1 should be in order to get the required output as the voltage regulated. So, this is normally put externally, this network is put externally, R 1 R 2 network is put externally in order to fix the output voltage, regulated voltage as what you want given V z. So, in every IC regulator also V z is specified, so that you can fix according to your own requirement what the output voltage should be. If this is the structure that is there in this thing, let us understand this structure fully. This is V naught and this is taking a current of V naught by R L, that is the load current, and this takes a current of, assuming that the transistor beta is high, this will take a current of V naught by R 1 plus R 2. Obviously, R 1 plus R 2 should be chosen by us such that this V naught by R 1 plus R 2 forms a small part of the load current, because the rest of the current should not be dominant for efficiency, for maintaining good efficiency. So, this is made small compared to V naught by R L, but this should be larger. Okay. V naught by R 1 plus R 2 should be much less than R L. This is one requirement. Then we have assumed that this current is V naught by R 1 plus R 2, that means this base current is neglected. That means this should be greater than, much greater than the base current. So, selection of R 1 plus R 2 is based on these requirements. Okay. It should be much greater than base current and it should be much less than the load current. And R 1 by R 1 plus R 2 ratio is fixed depending upon the output voltage. So, R 1 and R 2 get uniquely fixed based on this. Next, this current is nothing but V naught by R L plus V naught by R 1 plus R 2. Now, that current divided by beta that is the current delivered by the base of this. Let us see what this current is. This is at V I, well, we know this potential, and this is V naught, this is at V naught plus V gamma. So, the current in RC, this current is V I minus V naught, okay, minus V gamma by RC. So, this current keeps fluctuating as V I is changing. One thing is, this current has to be much greater than this current. This current is the one which is split between this and the transistor. So, V I minus V naught minus V gamma by R C this current should be much greater than, right, V naught by beta R L. Of course, this current can be ignored. Now, by how much greater? In the sense, this current should be capable of supplying this current, and also there should be some current left out for this transistor to be in the active region. That means, this current should not also go too high or too small. It should be high enough so that it can give some current to this and some current to this, so that this current transistor does not go off. If this keeps on increasing, this current remains the constant because O naught is constant. Rest of the current should go into this, and this current can keep on increasing. So, what will happen? This transistor will conduct more and more, and ultimately it will carry only a current of I naught. That means, it is capable of driving this transistor to off state. So, in the working of this regulator, we have to understand clearly, okay, the limitations on input voltage. Now, for a certain load here and output voltage, this current is constant. Let us say this current is 100 milliamperes and beta is 100, let us say. So, the base current is a constant requirement of 1 milliampere. So, this current has to be greater than 1 milliampere. Let us say it is 2 milliamperes for a given input voltage. So, this 1 milliampere will go into this. Therefore, I naught has to be greater than 1 milliampere. So, that some current is left out for this transistor to remain in the active region. So, as Vi keeps on increasing, this current will keep on increasing, and this current will keep on increasing, and this will keep on decreasing. So, for a certain limiting value of Vi, okay, this transistor will stop, differential amplifier will stop function, because it will reach the limit of its current switching. Again, when Vi is kept on decreasing, right, this current will go to 0, that is the other. So, because of this limitation itself, we will have a Vi max and Vi minimum that we can determine from these equations, right. So, this current, okay, should be much greater than this, and it should be less than I naught. Okay. This is the requirement. So, as far as this structure is concerned, we can as well put a current source here instead of RC, so that the open loop gain of this differential amplifier is high. Otherwise, the gain of this is simply GM RC by 2. The gain of this is GM RC by 2. GM is 1 over RE of the transistors. So, all these things you can assume as long as the current division is I naught by 2 and I naught by 2. Okay. That I naught by 2 division occurs only for a specific Vi situation. Okay. Otherwise, these two currents will be different, and the GM of the thing is 1 over, okay, RE1 plus RE2, okay, and the gain is that GM into RC by 2. RE1 and RE2 will depend upon the current sharing in this. So, all these things you have to remember, because it depends upon the operating point. The small signal definition of the equivalent circuit is based on the operating point, and it is not necessary that this should operate at all times, okay, with equal division of current here. So, this is a DC amplifier actually. Voltage regulator is using a DC amplifier for regulation purposes, and therefore, the operating point keeps on shifting as far as this is concerned. Okay. So, we will perhaps work out an example of this regulator and see for ourselves all the limitations that can come about in this circuit. And as far as the output impedance is concerned, since this is using an op amp in the negative feedback structure, it is much lower than the earlier output impedance, which was nothing but Re, okay, and Re plus Rz by beta plus 1. Here it will be much lower than that, it will be lower than the earlier impedance by the loop gain. Okay. So, we will work out an example and show the various parameters associated with the regulator. So, now consider example 22. For the voltage regulator circuit shown here, determine all the important parameters which we have already defined earlier. So, this is very illustrative of what exactly happens in a typical voltage regulator circuit. Vi is the applied unregulated voltage, which is, let us say, changing from 20 to 30 volts. This is the typical variation possible, because normally this unregulated voltage is derived from the power line, right, and that much variation occurs, okay, in the power line, and you are deriving from rectifier, transformer, rectifier, okay, filter, and unregulated voltage which is going to supply to this. So, that is varying from 20 to 30. You want a regulated supply voltage of, let us say, in this case 14 volts, because this is Vz is 7 volts and R2 is taken as equal to R1, okay, 10K 10K. So, 1 plus R2 over R1 is 2. So, 2 times 7 volts is the output voltage. So, regulated output voltage is 14 volts, okay, 2 times Vz, that is gone. And let us say RL, we would like to now know how much current I can draw before this circuit starts failing, stops functioning as a voltage regulator. First of all, is there a minimum current, is there a maximum current, etc. So, the current drawn here is V naught by RL. So, it keeps changing depending upon RL. The question that we would like to pose is, what will be the limitations on RL during which this will continue to function for an input voltage which is changing from 20 to 30 volts. Let us now see other bias currents that are going to flow through this, whether our design is properly done. 7 volts is here and the voltage across this biasing arrangement is 7 volts minus the 0.6 volts drop here for the diode connected transistor. This is a current mirror, okay, 0.6 volts drop here. So, 7 minus 0.6 is 6.4, okay, divided by 5.4. We will change this resistance suitably so that our current is some round number, otherwise we have to use calculator. Okay. 7 volts minus 0.6 is 6.4 volts, and across 6.4 K we have 1 milliampere drawn here. This 1 milliampere is a constant current that is going to be drawn, and therefore, this is going to be 1 milliampere. That is made independent of the input voltage variation. If we have connected this here, it would have varied. We do not want that to vary. So, this current is made constant, bias current is made constant by connecting it here. So, this current of course keeps varying here. This is the bias current needed for the Zener. Please remember, this has to be greater than 1 milliampere here, this current, so that some current is left for the Zener. Okay. This current is going to supply the Zener as well as this 1 milliampere. Okay. So, meanwhile, we are ignoring the current drawn by the transistor, of course. So, this current is going to be Vi, which is varying from 20 to 30 divided minus 7 volts divided by 10 K. So, basically this current is varying from let us say 20 minus 7 is 13, okay. 30 minus 7 is 23 by 10 k. So, it is varying from 1.3 milliamperes to 2.3 milliamperes. So, this current is varying, corresponding to this is 1.3 milliamperes, corresponding to this is 2.3 milliamperes. Let us keep a note of this, because when 1.3 milliamperes is flowing, okay, this 1 milliampere is taken away, the Zener is left with 0.3 milliampere. So, this current is going to vary from 0.3 milliamperes to 1.3 milliampere. So, that information is very useful for us. Okay. When it is changing from 0.3 milliamperes to 1.3 milliamperes, obviously the Zener voltage will change. It will not be constant at 7 volts. That change in Zener voltage is what is going to appear at the output as 2 times that. So, let us say at 0.3 milliamperes it is some value 7 volts, and 1.3 milliamperes it is 7.1 volt, okay, higher. Okay. Then correspondingly output will be changing from 14 to 14.2 volts. So, that is what is called as line regulation, right. So, as Vi is changing, output voltage is changing. So, you can therefore find out the line regulation factor as 14.2 minus 14, okay, divided by 14, okay, expressed as a percentage. So, that is the line regulation factor for this circuit. So, line regulation, okay, can be found out from the information about Zener voltage change here. So, let us say this at 0.3 it is 7 volts Zener, and this at 1.3 is 7.1 volt. Okay. So, output voltage is going to change from 14 volts to 14.2 corresponding to this. So, line regulation factor is going to be 14.2 minus 14 by 14. Okay. So, that is equal to 0.2 by 14 expressed as a percentage, that means that into 100. So, it is really 20 by 14 or 10 by 7, okay, which is 1 point, how much is it? Huh? Yeah, 1.4%. Okay. So, that is what is called as line regulation factor for this circuit. So, please understand this is one way, because of line voltage variation output voltage can vary direct. Other way is also through the link here, because this is not a truly very high impedance point, this there is a reverse bias junction here, then it is connecting. So, if the reverse bias impedance, okay, is not too high, then there will be transmission on this side also. So, all these factors will come into picture, but the primary factor in this circuit I told you, because compared to this impedance, this is very low, and therefore, most of the transmission occurs through this path, right. Next, we will also know what is the variation of current that is occurring here. That is, this we had mentioned about earlier. Because Vi is changing from 20 to 30 volts, the current here is changing. What is the voltage here? This is 14 volts, okay, and this is 14.6, let us say, V gamma more. So, this voltage is going to change, this is going to change from 20 to 30. that means this voltage across this is going to change from, let us say 5.4 to 15.4 volts. So, the current is correspondingly going to change from 5.4 by 15 to 15.4 by 15. What is the value? Current is going to change, that is most important for us, 5.4 by 15 to 15.4 by 15 milliamperes. So, one is this is 0.36 milliamperes and the other one is 1.03. So, the 0.36 to 1.04 something like that. Right. So, this is the variation of current in this. Now, what is the current demanded by this is what is important, so that we can find out how this works here. Now, this load is going to change, let me say. To what extent we can change the load, so that this circuit still functions. This is an interesting point, so that you see exactly how this circuit functions, trying to maintain 14 volts here. So, the current in this is 14 by RL. So, 14 by RL, okay, plus of course 14 by 20 K, right, this current 14 by RL plus 14 by 20 K, 1.03, okay, that does not matter, okay, not much of a change. So, 14 by RL plus 14 by 20 K, which is how much? This is 0.7 milliamperes. So, what should be the range of variation of RL, so that this transistor, this circuit still functions satisfactorily? This divided by beta, beta is given as 200. So, this divided by beta, this becomes a very small part of the current, you can see. Okay. Now, we have to concentrate on this 14 by beta RL. So, this current is being delivered here, base current of this. Now, let us consider it should keep functioning at all times, let us say. This current is changing from 0.36 to 1.03. The current required for biasing this is totally equal to 1 milliampere. So, when this is 0.36, what can happen? Let us see. When this current is 0.36, okay, what can happen? This can demand most of it, right. So, and therefore, this is left with almost nothing. Okay. So, that means 0.36 is going to be one limit of current, okay, where this is left with almost nothing and this 0.36 straight away going into this. That means 0.36 into beta, that is 200, is the maximum current this can deliver. Okay. So, this current can be equal to 0.36 at the limiting situation, or into beta, that is 36 into 2, 72 milliamperes, right. That is the maximum current it can deliver under that situation. If you demand more, there is nothing to give that. Under the situation that this is 0.36, that corresponds to input voltage of 20 volts. So, you can now see that RL should be greater than some value, because this you can now find out 14 by RL should be equal to 72 minus 0.7, that is 71.3. So, RL should be greater than 14 by 71.3. Okay. That this is in terms of kilo ohms K. So, roughly this will be equal to about 200 ohms. How much is it? 196. So, this is equal to 196 ohms. That means RL has to be greater than this. If it is less than this, this circuit will stop functioning for input voltage of 20 volts. Okay. Obviously, it will happily work if RL is 196 ohms with 2.3 milliamperes, that is not 30 volts, because 30 volts corresponds to 1.03 and this is demanding only 0.36, rest of it can go into this, that is 1.03 minus 0.36, whatever it is, that is about 0.64 can go into this very happily, because it still has some current to be given to this, that is 0.36, right. So, this circuit will function up to this kind of load, right. Lower than this, it will stop functioning. Now, we can also determine the maximum limit, that is RL max, because that will deliver the lowest current. Obviously, can we see whether it can be open circuited? We will see. Suppose RL is open circuited, nothing is demanded from it. Okay. Then what happens is this current is 0, the only current that is to be supplied is 0.7 milliamperes for this biasing circuit. 0.7 milliamperes divided by 200 is extremely small. Okay. So, most of the current in this will go into this. That is all right as long as it is 0.36, because if this 0.36 goes here, 0.64 will go into this, no problem. But if 1.03 goes into this, there is a problem, because only 1 milliampere should have gone right here, and there is nothing that will take the rest of the current. So, that means it has to deliver the rest of the current to this. Okay. That means it is not possible to have open circuit here. So, there is a maximum value for RL also. So, we will find out that. So, we have 14 by RL divided by beta plus 0.7 becoming equal to, let us say it is 1.03 here, because it is of no consequence to discuss it for 0.36, 1.03 when it is highest here, right, 1 milliampere is taken from this, 0.03 will go to this. If 0.03 goes, 200 times that will appear there, that means 6 milliamperes will be appearing there. Okay. So, this current can be at the limit equal to, lowest value is 6 milliamperes. 0.03 comes here into 200 is 6 milliamperes. Okay. So, this 14 by RL, okay, this beta is already taken, 14 by RL plus 0.7 milliamperes is equal to 6 milliamperes, or this is 5.3 milliamperes, or RL should be, okay, less than, okay, this 14 divided by 5.3 K. 2.64. That means we could have done this more easily, a better design would have been to select this R1 R2 combination itself as 2.6 K. So, there is no question of our, right, not 2.6 K, 2.6 K parallel 20 K, whatever resistance that is. That R1 plus R2 itself could be that. Okay. So, that we do not have to worry about this lower limit at all, we can keep it open. That is one way of designing, or you restrict the load resistance to change from 2.6 K to 196 ohms. Okay. So, load resistance can vary for this particular problem from 196 ohms to 2.6 K before it starts malfunctioning. Okay. So, let us consider that the load under consideration normally is a constant, let us say. Let us discuss other parameters for a constant load. Okay. This is the variation of load. Okay. And you can also plot, okay, load regulation by varying only this kind of resistance, because load regulation becomes meaningless beyond this range. Okay. Vary the load from 196 ohms to 2.6 K and find out how output voltage varies, okay, with respect to this variation of load. Okay. So, you can plot that characteristic, which will be looking almost as 14 volts constant, right. This load current is changed from let us say corresponding to RL equal to 196 to this is the maximum current, this is the minimum current, right. So, this variation you have to plot. This may be very small variation that is going to occur primarily once again as the low if this input voltage is kept constant, okay, this variation is going to be occurring because of the non-idealities of this differential amplifier that we have, that is going to be extremely small. That is, we are assuming that the voltage difference is 0, it is not strictly 0, right. So, the error voltage is 0 is what is assumed. So, the error voltage keeps changing as the load changes, because the operating point keeps shifting. So, the error voltage keeps changing, and therefore, that error voltage variation will appear at the output as the variation in the output voltage. Okay. So, that you have to determine experimentally physically, because this is a nonlinear phenomena here. Voltage is the load current is varied over a large range, and the operating point keeps shifting, and we have to find out how much the error voltage changes. So, based on this we can obtain the load regulation characteristic, and as far as the other parameters are concerned, like output impedance, this can be evaluated only for a specific load. Let us take the load as, let us say, for making matters simple, 14 K. Is it possible? No, we cannot take, because we can take it as, let us say, 2 K between 2.6 and 196 2 K. So, the current here is 7 milliamperes, and this is again 0.7 milliamperes. So, the total current here is 7.7 milliamperes. This is 7.7, and therefore, the base current is 7.7 divided by 200, which is going to be 0.038, okay, 0.038 milliamperes, correct, 0.07 divided by 0.038 milliamperes. Let us assume that this is nominally fixed at, let us say, 25 volts. 25 volts. So, if this is fixed at 25 volts, this is 14.6. So, this is 25. 25 minus 14.6 is the voltage, which is 10.4. Okay, 10.4 by 15 K. How much is it? 0.69 milliamperes. Now, for a 25 volts here, this is 14.6 volts, the current is 0.69, out of which only 0.04 goes, let us say this is 0.04. So, what is remaining here is 0.65. Okay. So, this will have 0.35 milliamperes. So, these will give us an idea about the operating currents of each of these. This is going to be how much? 25 minus 7, that is 18 by 10 K, 1.8 milliamperes. So, these are the operating currents. Now, how do we fix the output impedance? Okay. First, let us find out the open loop gain of this structure. Okay. Open loop gain before feedback factor beta in this case is half, 10 K 10 K. Okay. So, R1 by R1 plus R2 is half, and open loop gain is going to be GM. Okay. Now, GM is to be evaluated RE1 plus RE2, 1 over that is GM. So, VT divided by IE. Okay. IE1 is 0.35, IE2 is 0.65. So, 25 by 0.35, how much is it? 25 by 0.35 is 71.4 plus 25 by 0.65, 25 by 0.65. 38.46. So, this is the GM of the transistor stage, that into RC by 2, because single ended this is this thing, right. This need not be divided by 2, because this is the total resistance. So, this is the GM, okay, into RC. Okay, RC is 0.15 K. Of course, please remember that this 2 K is shunted by 20 K. So, 20 K effect can be ignored. So, this load is 2 K, and this 2 K will appear here as 2 K into 200. So, 400 K, but compared to 15 K, 400 K also can be ignored. So, essentially it is 15 K, otherwise you have to take the loading effect of this into account in evaluating the open loop gain. So, this is 15 K RC. So, that is the open loop gain. This is 15 K by this total, which is 0.86909, 110 about. So, no, what is the this thing total? 15,000 divided by this thing, that means about 150. Huh? 136.36. 136. That is the open loop gain. That into beta. Okay. This is, let us say, A naught. So, A naught beta is going to be half of 136, 68. Okay. So, the original output impedance is going to be decreased by a factor of 1 plus loop gain. That is what we have learnt in our earlier lecture, right. So, original output impedance is this RE, okay, plus 15 K divided by beta. Without any feedback, it is simply RE, okay, plus 15 K by beta, apart from the shunting effect of this, right. So, essentially original output impedance without feedback is going to be RE Re is 25 by 7.7 ohms, okay, plus 15K divided by 200. So, you can notice that it is essentially 75 ohms plus about 3 ohms, okay, 25 by 8, about 3 ohms, that means 78 ohms. Right. So, this has to be divided by with feedback (78) divided by 69 ohms. How much is this? Very nearly 1 ohm, okay, and that is the output impedance. 1.1. So, this is the kind of output impedance of the structure. One thing that you have to remember is this is a feedback structure, and that is why it is giving pretty low output impedance. If you use an op amp, it can become fractions of ohms, but that is valid only for low frequencies. At high frequencies, you cannot assume this kind of gain, the loop gain reduces and output impedance increases. This has to be borne in mind, because this regulator may be used for high frequency applications. So, output impedance is important only for high frequencies, low frequency output impedance is of no significance, right. So, how much the circuit that is being supplied this power is seeing, that impedance becomes important only at the frequency at which the circuit is functioning. Okay. This is functioning at low frequency, this is a DC regulator, okay, and therefore, output impedance on the other hand is important only looking at this circuit from the circuit that is using this as a power supply. Okay. So, that circuit may be working as an oscillator at, let us say, 1 megahertz, then you have to evaluate the output impedance at 1 megahertz for this circuit. So, that may not be purely resistive. Okay. So, that output impedance may become pretty high and it may cause problem, okay, unless you purposely reduce it using special technique. Like now, this if it does not use an op amp, the output impedance at low frequency will be almost same as output impedance at high frequency. On the moment you use an op amp, okay, that gets drastically changed. So, output impedance is evaluated. You can also evaluate the ripple rejection by replacing the whole by its equivalent circuit, okay, and varying this voltage by a small extent and finding out what this voltage is. Or most of the ripple rejection occurs because of this, that when there is a ripple, there is a transfer here which is going to be Rz divided by Rz plus 10K. And that will be simply multiplied by a factor of 2. Okay. So, the ripple rejection is going to be due to this fact that Rz by Rz plus 10K into 2, okay, is the ripple rejection factor, expressed as a percentage is really what is normally indicated as ripple rejection. So, these are the important parameters associated with this. Apart from that, we can also find out the efficiency. Efficiency here is essentially 14 by 25. I have told you that it is just ratio of output voltage by input voltage. 14 by 25 is the efficiency of this.